Hi, welcome to Supervised Learning with scikit-learn. Here you get a chance to grow your machine learning skills with scikit-learn and discover how to use this popular Python library to train models using labeled data. In this course, you'll learn how to make powerful predictions, such as whether a customer will churn from your business, whether an individual has diabetes, and even how to classify the genre of a song. Using real-world datasets, you'll find out how to build predictive models, tune their parameters, and determine how well they will perform with unseen data. This course consists of 4 chapters, which are classification, regression, fine-tuning your model, and lastly, pre-processing and pipelines. In this video, we will be covering Chapter 1, Classification. Here we'll be introduced to classification problems and learn how to solve them using supervised learning techniques. You'll learn how to split data into training and test sets, fit a model, make predictions, and evaluate accuracy. You'll discover the relationship between model complexity and performance, applying what you learned to a churn dataset, where you will classify the churn status of a telecom company's customers. We will be learning the basics of machine learning with scikit-learn, moving on to the classification challenge and then measuring model performance. Machine learning is the process whereby computers learn to make decisions from data without being explicitly programmed. For example, learning to predict whether an email is spam or not spam given its content and sender, or learning to cluster books into different categories based on the words they contain, then assigning any new book to one of the existing clusters. Unsupervised learning is the process of uncovering hidden patterns and structures from unlabeled data. For example, a business may wish to group its customers into distinct categories based on their purchasing behavior without knowing in advance what these categories are. This is known as clustering, one branch of unsupervised learning. Supervised learning is a type of machine learning where the values to be predicted are already known, and a model is built with the aim of accurately predicting values of previously unseen data. Supervised learning uses features to predict the value of a target variable, such as predicting a basketball player's position based on their points per game. This course will exclusively focus on supervised learning. There are 2 types of supervised learning. Classification is used to predict the label, or category, of an observation. For example, we can predict whether a bank transaction is fraudulent or not. As there are 2 outcomes here, a fraudulent transaction, or non-fraudulent transaction, this is known as binary classification. Regression is used to predict continuous values. For example, a model can use features such as number of bedrooms, and the size of a property, to predict the target variable, price of the property. Note that what we call a feature throughout the course, others, may call a predictor variable or independent variable. Also, what we call the target variable, others may call dependent variable or response variable. There are some requirements to satisfy before performing supervised learning. Our data must not have missing values, must be in numeric format, and stored as pandas data frames or series, or NumPy arrays. This requires some exploratory data analysis first to ensure data is in the correct format. Various pandas methods for descriptive statistics, along with appropriate data visualizations, are useful in this step. In this part of the tutorial, we are going to do a practical example of using scikit-learn, which is a machine learning library for the Python language. Links to web pages and datasets used in the upcoming slides are given in the description of this video. To get started, first download the latest Python from the official website you can see in this screenshot. Next, you need an integrated development environment, IDE. I would recommend using PyCharm Community Edition, which is a Python IDE, but you can also use any other tool of your choice which supports Python development. After downloading PyCharm, install it and create a new project with configurations you can see in this screenshot. For working with scikit-learn, you will have to install the scikit-learn library from the Python package index website you can see in the screenshot. Just copy the pip command and execute it in the terminal window inside IDE you can see in the screenshot. Next, you will have to import the sklearn datasets and call a function to show its output. Previously, we learned that supervised learning uses labels. Let's discuss how we can build a classification model, or classifier, to predict the labels of unseen data. There are 4 steps. First, we build a classifier, which learns from the labeled data we pass to it. We then pass it unlabeled data as input, and have it predict labels for this unseen data. As the classifier learns from the labeled data, we call this the training data. Let's build our first model. We'll use an algorithm called k-nearest neighbors, which is popular for classification problems. The idea of k-nearest neighbors, or KNN, is to predict the label of any data point by looking at the k, for example, 3 closest labeled data points and getting them to vote on what label the unlabeled observation should have. KNN uses majority voting, which makes predictions based on what label the majority of nearest neighbors have. Using this scatter plot as an example, how do we classify the black observation? If k equals 3, we would classify it as red. This is because 2 of the 3 closest observations are red. If k equals 5, we would instead classify it as blue. To build intuition for KNN, let's look at this scatter plot displaying total evening charge against total day charge for customers of a telecom company. The observations are colored in blue for customers who have churned, and red for those who have not churned. Here we have visualized the results of a KNN algorithm where the number of neighbors is set to 15. KNN creates a decision boundary to predict if customers will churn. Any customers in the area with a gray background are predicted to churn, and those in the area with a red background are predicted to not churn. This boundary would be used to make predictions on unseen data. For next couple of practicals, you need 2 more libraries, NumPy and Pandas, which are given in the screenshots you can view. Just copy the names of these libraries and install them using pip. You can view the screenshot how to install the 2 libraries before you can import them in your next code practice. To fit a KNN model using scikit-learn, we import the k-neighbors classifier from sklearn.neighbors. We split our data into features, a 2D array of our features, and target var, a 1D array of the target values, in this case, churn status. Scikit-learn requires that the features are in an array where each column is a feature and each row a different observation. Similarly, the target needs to be a single column with the same number of observations as the feature data. We use the .values attribute to convert features and target var to NumPy arrays. Printing the shape of features and target var, we see there are 3,333 observations of 2 features, and 3,333 observations of the target variable. We then instantiate our k-neighbors classifier, setting n_neighbors equal to 15, and assign it to the variable knn. Then we can fit this classifier to our labeled data by applying the classifiers.fit method and passing 2 arguments, the feature values, namely features, and the target values, target var. Here we have a set of new observations, test_data. Checking the shape of test_data, we see it has 4 rows and 2 columns, that is, 4 observations and 2 features. We use the classifiers.predict method and pass it the unseen data as a 2D NumPy array containing features in columns and observations in rows. Printing the predictions returns a binary value for each observation or row in test_data. It predicts 1, which corresponds to churn, for the last observation, and 0, which corresponds to no churn, for all other observations. Now we can make predictions using a classifier, but how do we know if the model is making correct predictions? We can evaluate its performance. In classification, accuracy is a commonly used metric. Accuracy is the number of correct predictions divided by the total number of observations. How do we measure accuracy? We could compute accuracy on the data used to fit the classifier. However, as this data was used to train the model, performance will not be indicative of how well it can generalize to unseen data, which is what we are interested in. It is common to split data into a training set and a test set. We fit the classifier using the training set, then we calculate the model's accuracy against the test set's labels. To do this, we import train test split from sklearn.model_selection. We call train test split, passing our features and targets. We commonly use 20 to 30% of our data as the test set. By setting the test size argument to 0.3, we use 30% here. The random state argument sets a seed for a random number generator that splits the data. Using the same number when repeating this step allows us to reproduce the exact split in our downstream results. It is best practice to ensure our split reflects the proportion of labels in our data. So if churn occurs in 10% of observations, we want 10% of labels in our training and test sets to represent churn. We achieve this by setting stratify equal to target var. Train test split returns 4 arrays, the training data, the test data, the training labels, and the test labels. We unpack these into features train, features test, target var train, and target var test, respectively. We then instantiate a KNN model and fit it to the training data using the .fit method. To check the accuracy, we use the .score method, passing features test and target var test. The accuracy of our model is 87%, which is low given our labels have a 9:1 ratio. Let's discuss how to interpret K. Recall that we discussed decision boundaries, which are thresholds for determining what label a model assigns to an observation. In the image shown, as K increases, the decision boundary is less affected by individual observations, reflecting a simpler model. Simpler models are less able to detect relationships in the dataset, which is known as underfitting. In contrast, complex models can be sensitive to noise in the training data, rather than reflecting general trends. This is known as overfitting. We can also interpret K using a model complexity curve. With a KNN model, we can calculate accuracy on the training and test sets using incremental k values, and plot the results. We create empty dictionaries to store our train and test accuracies, and an array containing a range of k values. We use a for loop to repeat our previous workflow, building several models using a different number of neighbors. We loop through our neighbors array and, inside the loop, we instantiate a KNN model with n neighbors equal to the neighbor iterator, and fit to the training data. We then calculate training and test set accuracy, storing the results in their respective dictionaries. After our for loop, we then plot the training and test values. Here's the result. As k increases beyond 15, we see overfitting where performance plateaus on both test and training sets, as indicated in this plot. The peak test accuracy actually occurs at around 13 neighbors. Thanks for watching. In the next video of the playlist, we will be introduced to regression, and build models to predict sales values using a dataset on advertising expenditure. You will learn about the mechanics of linear regression and common performance metrics such as R-squared and root mean squared error. We will perform k-fold cross-validation, and apply regularization to regression models to reduce the risk of overfitting. Also, if you have any questions, you can ask them in the comments section and we'll be pleased to answer those for better level of understanding. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.